Good morning, Jordan. This is number 1, C, D, and E on your exam practice number 3. And in E, you're basically asked if the results suggest, that money can be saved by making smaller manholes with a diameter of 19 inches or 18.5 inches. Well, the first thing you have to notice in C is that we're looking at the shoulder breadth of the men that are going to go into those manholes. And so we're looking at the probability first in C that the shoulder breadth will be less than 19 inches, and then in D that the shoulder breadth will be less than 18.5 inches. It all goes back to the fact that we're told that we can assume that the shoulder breadth of these men are normally distributed with a mean of 18.2 inches and a standard deviation of 1.1 inches. The thing is, though, we're taking a sample of 36 men. So what we have to do is recalculate the standard deviation. It's called the standard deviation of our sample averages. And we do that by taking the standard deviation of the population and dividing by the square root of our sample size. So in our case here, the standard deviation of the population of these men is 1.1, and we're dividing by the square root of the size of our sample, 36. So if you take 1.1 and you divide by 6, which is the square root of 36, you get a standard deviation of about 0.183. It's actually 0.183 repeating. So what I've done here in this normal curve to try to help you visualize this is this normal curve should be centered at 18.2 inches, and every standard deviation to the right of it I should add an additional 0.183 inch, and every standard deviation below the mean of 18.2 I should subtract 0.183 inch. And so now what I can see is that a 19-inch shoulder breadth is way up here somewhere, way further than 18.75. So I'm more than 3 standard deviations above the mean. So the first thing you notice you need to do whenever you're in a normal distribution then is to calculate the z-score, which basically just tells you how many standard deviations from the mean this value is. And the formula we use to calculate that z-score is take your average that you're looking at, our sample average, x bar in this case is 19. This is part C, by the way. Subtract the mean given of 18.2, but divide by what's called the standard error of that mean, what we got when we divided sigma by root n, and that's our 0.183. Well, when you calculate that value, you get, depending upon how you rounded, you get something close to 4.36 standard deviations above the mean. So that seems reasonable based upon our picture. In our picture, we recognize that it was definitely more than 3 standard deviations above the mean. Now we see it's actually more than 4 standard deviations above the mean. When you go to your table of standard normal probabilities and you look up a z-score of 4.36, you find that 4.36 is not even on your table. That's because it's so far out there. So your table then in the bottom lower left-hand corner, somewhere near the bottom I remember, tells you that anytime you get a z-score greater than 3.49, then use the area below of 0.9999. And so we're going to approximate the area below a 19-inch shoulder breadth for a man who's going to go into these manholes is equal to almost 100%. So then you'll notice in D, we're going to need to do the same thing. This time, though, in D, we're looking at a man whose shoulder breadth is 18.5. Well, even though that's only a half-inch difference, we can see from our picture that 18.5 is much closer to the mean in standard deviations. It appears to be between 1 and 2 standard deviations. And actually, it is 1.64-ish, depending upon how you rounded, standard deviations if you do the same thing, but this time use an x-bar of 18.5. So the probability then that z will be less than 1.64 can be found in your table. So when you go to your table, you go to the far left column and you follow that column down to a z-score of 1.6. Then you have to move to the right to the column that has a 0.04 at the top of it, since we have a 4 in the hundredths column here. And when you do that, you find that the area below, that table always gives area below or proportion below, is equal to 0.9495. So let's try to picture this a little bit further. What we've just determined is that the area below that blue line that I drew there is equal to about 0.9495, and in C, we determined that the area that is below that red line that I drew is much greater. Well, not much greater, but it is greater, equal to about 0.9999. So in other words, we've determined that it is more likely that we'll find a man whose shoulder breadth is less than 19 inches than it is to find a man whose shoulder breadth is less than 18.5 inches. Now, initially then, you're thinking, okay, 95% of the averages of a sample of 36 men, 95% of those sample averages will have shoulder breadths that will be less than 18.5 inches, which would end up being less than 19 inches, meaning, yeah, a high percentage of our sample averages from samples of size 36 will have men that will be able to fit inside of this 19-inch manhole. The problem is that we've calculated the probability that the average of a sample of 36 men will fit inside the manhole. We haven't looked at the probability that a single man will fit inside the manhole. So you notice then when you look at your professor's answer key, he then goes on to find the probability of a single man having a shoulder breadth of less than 19 inches, and then finds the probability of a single man having a shoulder breadth of less than 18.5 inches. And I'm going to show some of those calculations on my next slide. So we're glad to know that a high percentage of sample averages from samples of size 36 men can fit inside the 19-inch manhole. But we're more interested not in averages of a sample, but how well are the men in general, individually, going to fit inside the manhole. So we're going to look at individual men. And when we look at individual men, then we have to consider that our standard error of our sample averages now, when we take sigma and divide by root n, if we're looking at individual men, we're going to be taking our standard deviation of the population of men and dividing by root 1. So we're dividing by root 1, which means we're dividing by 1, so our standard error now is much greater. It's 1.1 inch. So I've numbered my new normal distribution for individually selected men, counting by 1.1 inch above the mean. I didn't do any counts below because both 18.5 inches and 19 inches are above. So let's start with the 19 inches again. I'll mark it in red as I did on the previous slide. 19 inches is about here. And you can see in the calculations, the z-score for 19 inches now is going to be different. We can clearly see in our picture it's between 0 and 1 standard deviation above the mean. If we actually calculate it, if we take 19 minus the mean of 18.2 and divide by the standard deviation, we get a z-score of 0.72. And so if we look up that z-score in our table of critical values, the proportion of individual men who will have a shoulder breadth that is less than 19 inches, which in this distribution would mean less than a z-score of 0.72, the proportion below or less than is equal to 0.2327. Again, we had to go over to down to a z-score of 0.7 and then over to the column that has a 2 in the hundredths place, since we have a 2 in the hundredths place here, and we see that 0.7642. No, we don't. I see where you might have some confusion. All right, what we see when we look this up in our table is 0.7642. I'm going to take a look at your professor's notes. Okay, first of all, I would round this to 0.73 because it does come out to be 0.727272 and so on. So looking at the table, when we look up the area below 0.73, Jordan, we go down to the 0.7 and over to the 3 in the hundredths column, and we get 0.7673. Now, if we think about that, that represents the red area in our table, and basically we've determined that the probability that an individual man will have a shoulder breadth of 18.5 inches or less is 0.7673. Now, when we identify the location in this distribution of a man who has a shoulder breadth of 18.5, it would be closer to the mean. If we calculate that z-score using the same formula, we get a z-score of 0.27. So when we look up that proportion of men who will have a z-score of 0.27 or less, we see in our table that that proportion would be equal to 0.6064. So basically this blue area here is equal to about 60.6%, a little smaller than the total red area that it overlaps. So the question now is, do these results suggest that money can be saved by making smaller manholes with a diameter of 19 inches or a diameter of 18.5 inches? So we're talking about the fact that we need these men to be able to fit in these holes. What we know is that about 61% of men have shoulder breadths that are less than 18.5 inches. Well, that means that about 39% have shoulder breadths that are more than 18.5 inches. That's a little concerning. That's like every 4 in 10 men are not going to be able to fit in a manhole that is 18.5 inches, okay? On the same note, we found that the probability that a man has a shoulder breadth of 19 inches or less is about 77%, which means still about 23% are not going to be able to fit in the manhole. The manhole will be too small. And that's too great a risk. If you want all of your men in general that work in these manholes to fit in the manholes, it's too great a risk to go with a smaller manhole, which is why his response to part E was no. Hope that helps. Let me know if you have further questions.